Today we're doing Chapter 9, Section 6 in Math Analysis. This is polar form of complex numbers. I'm your host, Dr. D. Today, boys and girls, the phrase that pays, math rules. You'll know what I mean once you start looking for a job after you get a degree. Okay, let's get going here. So, you know what complex numbers are, and you know what polar form is. Now we're going to have polar form of complex numbers. What this means is we've got a coordinate system where the horizontal axis is the real numbers and the vertical axis is the imaginary numbers. So if I have the number 3 plus 2i, what that means is I just go right 3 and up 2. So the point is right there, 3 plus 2i, because it's 3 in the real and it's 2 in the imaginary. And notice, you can't mix real and imaginary. There's no such thing. You either go right or left for real and up or down for imaginary, and that's it. So let's check out a couple, the quadrantal angles are going to be either pure real or pure imaginary, and those are going to be important. So let's just start with 2. If I want the number 2, that's right there, 2, because it's 2 to the right. Now, you don't have to say 2 plus 0i, but that's really what it is. Now, what about 2i? Well, that's right here, 2i. And once again, you don't have to say 0 plus 2i, because it's just up 2. That makes it 2i on this plane. And so if we go straight left, that would be negative 2. And if we go straight down, that would be negative 2i. So pure imaginary, or pure real numbers are on the horizontal axis, and pure imaginary numbers are on the vertical axis. And any complex number is going to be in one of the planes. So if I wanted, let's say, negative 5 plus I. Negative 5 plus I just means left 5. Oh no, it's blue. How embarrassing. Left 5, 1, 2, 3, 4, 5, and up 1. So there is my negative 5 plus I. And then negative 5 minus I be in the third quadrant. So it's a piece of cake. So basically what we're doing here is instead of saying negative 5 comma 1, we're just saying negative 5 plus I. And so that's polar form. Well, I'm sorry. These are rectangular forms of complex numbers. Now if I want the polar form, then all I want is the magnitude and the angle. Okay, so let's look at our three plus 2i. Now, that's rectangular form. If I want the polar form to that, then what I want to do is find the length between the origin and the point and the angle. So basically what I have then is this is going to equal the magnitude is going to be, well, r is going to equal the square root of 3 squared plus 2 squared. Now notice it's not 2i squared, it's just 2 squared. We don't care about the I when we calculate r, because we're basically just trying to find the distance from the origin to the point. So this ends up being square root of 13. And the theta, just like we did before, is going to be the inverse tangent of y over x, or in this case, 2 over 3. Which is going to equal we'll put this in radians. So 0.588 radians. Now, we're going to name this point, instead of r comma theta, we're going to name it r cis theta. So it just becomes square root of 13 cis 0.588. What does cis mean? It means cosine plus I sine. So this is how the book is going to read it. Square root of 13 cosine 0.588 plus I sine 0.588. So notice, if I take the cosine of the angle, I'm getting the x coordinate. If I take the sine of the angle, I'm getting the y coordinate. The x coordinate is the real part. The y coordinate is the imaginary part. And actually, to be formal here, we actually do need to put the parentheses around it because it's square root of 13 times the whole thing. But I don't like writing cosine of the angle plus I sine of the angle. This is much more convenient. So we have rectangular form and we have polar form. Now, how do we get from, well, I just showed you how to get from rectangular to polar. All you do is Pythagorean theorem to get your r, and then inverse tangent to get your theta. How do we get back from polar to rectangular? Well, it says it right here. Cosine of the angle, multiply that by square root of 13, and you get the real, and then square root of 13 times sine of the angle, that'll get you your imaginary. So all we've done basically is substitute a comma for a plus and an I here. And then we've substituted a comma for cis, or cis for our comma. So instead of, before we were going r comma theta, which would be square root of 13 comma 0.588, now we're just going square root of 13 cis 0.588. Really is pretty simple, nothing new. We're going to get into some interesting uses of this in the next couple of sections, but for right now, it really isn't much new. Okay, now, first thing you're going to have in your homework is solving an equation for x and y. Now, the key thing here is the reals don't mix with imaginaries. So all you do is set it up a real equation and an imaginary equation and solve both. So let's check out an example of that. Okay, so 2x plus y plus 3i equals 9 plus xi minus yi. All right, there are really two separate equations here. There's the real, there's the imaginary. And like I said, they don't mix. So we just treat them like two separate equations. So the real is 2x plus y. Now we're in the real dimension. I don't even see this 3i. So it's just 2x plus y equals, what's real over here? Only 9. I don't see xi minus yi. They're in a different dimension. Okay, so now we're looking at the imaginary dimension. So we've got 3i, or I could just go 3 equals x minus y. Okay, so notice I have two equations now with x and y. So I can put them together and say, okay, 2x plus y equals 9, and I'm going to add x minus y equals 3. The y's drop out. I've got 3x equals 12, so x equals 4. Now, if x equals 4, then 4 minus y has to equal 3. So clearly y has to be 1. Now, notice I've got 8 plus 1 equals 9, and 3 equals 4 minus 1. Those both check. And so I can put it back up in the original equation then. And that basically says that 2x plus y plus 3i is going to equal 9 plus 4i minus what? Or minus 1i. Okay, so what's this say? Well, it says 8. Well, yeah, let's do that all in one step there. It says 8 plus 1, which is 9, plus 3i equals 9 plus 3i. So that checks. So this really is a piece of cake. Like, you could do this in Algebra 1. Okay. Next thing we're going to do is just graph numbers on a complex plane. So we've already done that. If I give you, let's say, -1 minus square root of 5i. -1 minus I square root of 5, I should say. How do you graph that on a complex plane? Well, we go, in the real direction, it's -1. In the imaginary direction, it's down square root of 5. So square root of 5 is about 2.3, so there it is. Piece of cake. Could not be easier. It's just like saying -1 comma negative square root of 5. And that's how you graph that. Okay. Next, we're going to, the other thing we're supposed to do is find the absolute value of that. So, what is the absolute value of -1 minus I square root of 5? Well, let's just do a general, absolute value is just the distance from the origin. So it's basically, what's the magnitude of that? But I'll give you a general formula is A plus BI. The absolute value of that is the square root of A squared plus B squared. Now remember, this is not BI squared, it's just B squared. So B is just the number that's attached to the I. It doesn't include I, so don't do that, or you will die an ignominious death. An ignominious death? That's never loud enough. Okay, so what is this going to equal? It's going to equal the square root of -1 squared plus negative square root of 5 squared. And the negatives aren't even important because you're squaring them, it's going to be positive. So this ends up being the square root of 1 plus 5, which equals the square root of 6. So basically the absolute value of this number is just saying what's the magnitude of the radius, the distance from the origin to the point is just going to be square root of 1 plus 5, which is square root of 6. Okay, that's easy. Now, next we're going to be given complex numbers and we want to put them in polar form. So complex numbers in rectangular form, put them in polar form. Okay, so let's try that. Get rid of this stuff. All right, 5 plus 3i. This is rectangular form. We want it in polar form. Now, we just did this in the beginning of the lesson. So it's just going to be the square root of 25 plus 9 is square root of 34 cis inverse tangent of y over x is going to be .540. That's it, piece of cake. All right, let's do a few more. What about one plus square root of 3i. Let's go 1 minus square root of 3i. Okay, so you really don't need a calculator for this because if you notice what's going on here, it's 1 right and square root of 3 down. So what's that magnitude? Right, 2. And what's the angle? Right, 5 power over 3. There it is. Now, if I was given 2 cis 5 pi over 3, all I would do is the x coordinate is 2 cosine 5 pi over 3, and the y coordinate is 2 sine 5 pi over 3 I. Now, let's do some more that we don't need calculators for. What about 2? Yeah, just plain 2. What is that in polar form? That's going to be 2 cis 0. Because we just said it's 2 straight right. What about negative 2? Well, that's just 2 cis pi. Because that's just 2 straight left. What about 2i? That's 2 straight up. What does that mean? 2 cis pi over 2. And negative 2i is just 2 straight down, so that would be 2 cis 3 pi over 2. So notice, we don't mess around with a squared plus b squared, take square root of it, then inverse tangent of the y over x, when it's just a real alone or an imaginary alone, all you do is say, which direction is it? Well, that's right. There's the angle to the right. That's left. There's the angle left. That's up. That's the angle up. And that's down. There's the angle down. So there is no such thing as having to make a triangle. It's just a quadrantal angle. So notice if it's a 30, 60, 90 or 45, 45, 90, you don't need a calculator for it. If it's a quadrantal angle, you don't even need a triangle for it. And if it's not one of our special right triangles, then just use Pythagorean theorem and inverse tangent. Piece of cake. All right, now the other way is if you're given a number in polar form, you need to change it back to rectangular form. So let's do 3 cis pi over 2. Well, what is that looking like? It's looking like 3 straight up. So once again, I don't need a triangle here. All I do is say, that's 3i. Okay, now, what if we have five cis pi over 4? Okay, that just equals 5 cosine pi over 4 plus 5i sine pi over 4. Now what's cosine pi over 4? Right, square root of 2 over 2. So we've got 5 square root of 2 over 2 plus, now this is going to be 5i times square root of 2 over 2. So technically the way we're supposed to write it is 5 halves I square root of 2. If you wrote it 5 square root of 2 over 2i, that wouldn't be horrible, but technically you're supposed to have the rational, then the I, then the irrational. So what about 17 cis negative pi over 3? What's that equal? Pretty soon you shouldn't have to be writing cosine and sine out because you know what that's what cis actually means. So what's cosine negative pi over 3? Let's look at that. Negative pi over 3 would be down here. And so this is, oops, that's positive 1. This is negative square root of 3. And this is 2. So I have to destroy all evidence that I screwed up. Okay, so cosine of this angle is going to be 1/2. So I've got 17 halves. And sine of this angle is going to be negative square root of 3 over 2. So it's minus 17 halves I square root of 3. So it's 17 square root of 3 over 2 times I. So that's it. It really is going to be simple. Okay, now the last thing we're going to do is the iterations. Basically, the fractal example. So take a look on page 587. I don't want to do this because it's going to be longer than it's going to be worth, but I just want to show you the first couple of steps. So if I know that z sub O is 0.9 plus 0.3i. Z sub O equals 0.9 plus 0.3i. And we're also given that f of z equals z squared. Yeah, that is right. Okay. So now, that's basically saying I'm just going to take any z and plug it in the function, square it, and get my new z. So z sub 1 is just going to be z sub o squared, which is going to equal 0.9 plus 0.3i squared. Now, that equals 0.9 squared plus 0.3i squared, right? Okay, thank you. Thank you very much. Okay, clearly we don't just square that and square that. We have a middle term. So we have a squared, which is 0.81, plus 2ab, so 2 times 0.9 times 0.3i, plus 0.3i squared. So this equals 0.81 plus, let's see, 2 times 0.3 is 0.6 times 0.9 is 0.54. So this is 0.54i plus 0.09 squared, or 0.09i squared. Now I squared is -1, so let's just go minus 0.09. Okay, so this is going to equal 81 minus 9, 72. So 0.72 plus 0.54i. All right, so that's z sub 1. Now, z sub 2 is just going to be z sub 1 squared, which equals 0.72 plus 0.54i squared. Now, like I said, I don't want to bore you with going through that. That's pretty mechanical. You're just going to square your 0.72 plus 2 times 0.72 times 0.54 times I, and then plus 0.54i squared, which would be minus 0.54 squared. And that ends up being 0.23 plus 0.78i rounded off. And then to get z3, you just plug it back in the formula and you get negative 0.55 plus 0.35i and so on. And you notice in the book then what they do is they graph each point, and you notice it makes a pattern. Now, the more points you have, the more interesting that pattern becomes. But we certainly don't want to graph points by hand. Most of those patterns are generated where you can do thousands of points with a high-speed computer. And then it's gorgeous. But that's basically it. Have fun with these.